Today's lesson is on piecewise function. I'd make a joke about the word piecewise, but making corny jokes when it sounds like you're making a joke to yourself are nowhere near as funny. Anyway, a piecewise function is a function made up of two or more rules on two or more intervals, which creates two or more parts on the graph of this function. It can have similar parts or not so similar parts. So for example, we could have a piecewise function that's made up of a bunch of linear models. So we have a line, and then it continues with a line, so that would be two linears, which would be similar, or it could be not similar. Maybe we get something that looks like a square root function, and then a part that looks like a parabola. Right, so those would be two different ones. Now, these functions, these types of functions, piecewise meaning, are often used to model situations such as parking fees, cell phone plans, etc. So when a rate changes partway through, then you'd have to use a piecewise function to model that situation. You can see the two examples I've drawn above are both discontinuous, right? We've got a break in both of them. But we can also have piecewise functions that are continuous, right? We could have one maybe that's made up of a set of lines, and the lines just change slope, right? So that would still be piecewise, but in this case it is continuous. Here we have an example of a graph that is a piecewise function, and I'm just going to show you how to write this function in function notation. So first we have to determine what each part of the graph is. I've labeled them for us just to make it a little bit easier. And we can see that the A segment here is a linear function, so we need to figure out the slope and the y-intercept to be able to write an equation for it. So you can notice here we can make our little triangle for slope that the rise is 1 and the run is 1, which means we have a slope here of 1. So our slope is 1, and we have to try to figure out what the y-intercept is going to be. So if we imagine this graph extending itself still at a slope of 1, it looks like it would pass through 2, so our slope must be, our y-intercept must be 2. Which means we could write an equation that matches this. Part A must be represented by the line y equals x plus 2. Not B. Okay. And then we have part B, which looks like it is the quadratic function, or at least part of one. Right? We're starting here at the origin, and it looks like it's gone over 1, up 1, and then over 2, up 3, and that is the model y equals x squared. And then finally, this last line here, part C, again looks like a line, so it's linear. It's a horizontal line, so the slope is 0. And the y-intercept, again, we'd have to extend the graph back to know. And that looks like it's 3 when it crosses. So we're going to say that the y-intercept for this is 3. And that means this line is y equals 3. So now we just have to put this together into our actual function notation. You'll see here I've used the kind of fun-looking brackets to start it out, and that's how it always looks like. So f at x is the defined function, and it's going to go into parts, and all those parts are going to be within this bracket. So our first one here is x plus 2, and we have to notice here that we're looking at this line only in a certain segment. So we notice here that that graph ended at -1, and there's a completed circle there, so we're going to say it includes -1. So this part is defined where x is less than or equal to -1. And segment B we determined was x squared. So that's going to be where we're going to go from -1, and since we already used -1 in the previous one, we're just going to say -1 is less than x, and it goes to a completed circle at +2, so that's going to be less than or equal to 2. And finally, this one is y equals 3, and this is for all of the remaining values of x. Notice it's an open circle for part C that then continues straight along, so that's why we're going to have it go from 2 like this.